Haga la transmisión en YouTube. Listo.
Hola, ¿qué tal a todos? Buenas tardes, desde donde nos estén acompañando. Estamos muy emocionados por participar en este primer Congreso de Educación STEM con Simulaciones PhET. Hemos tenido 2 días llenos de actividades maravillosas y hoy tenemos la perla de nuestro collar, ¿no? Tenemos como invitado a Carl Wieman, quien es ganador del Premio Nobel de Física hace ya varios años y fundador de este proyecto que es lo que nos hace estar todos juntos aquí, que son las simulaciones PhET. Aparte de ser un premio Nobel de Física, también fue el ganador del premio Girán de Educación, que es un equivalente, para que vean el alcance, un equivalente del premio Nobel, pero para investigación educativa. Entonces, hoy nos viene a presentar de qué se tratan estas investigaciones. Los últimos 20 años de su vida profesional ha enfocado a encontrar mejores formas para que las personas aprendan física y ahora viene a compartirlo con todos nosotros. Muchas gracias por acompañarnos y pues dejo el escenario a nuestro invitado estrella. Carl, el público es tuyo.
Okay, thank you. So it's a pleasure to talk to this conference, and I hope that translation works well. I'm going to talk to you about taking a scientific approach to science education. But before I start, I want to give you a little bit of my background of how I became involved in this education work and developing PhET, etc. And it actually started with my physics research. And a pattern I saw over many years of working in experimental physics with students, which is that these students would come into my laboratory with many years of success in physics courses and exams and so on, but they really didn't seem to be able to do physics when they were in the laboratory. But after just a couple of years of working with me, they turned into expert physicists. So there clearly wasn't something fundamentally wrong with them. And so after I saw this happen repeatedly, and particularly the students who seemed to be the best in their exams and courses never turned out to be the best physicists, I decided there was really a fundamental question here. And so I treated it really as a science question, and I started looking into research on how people learn, particularly how they learn physics. And from reading all that research after a couple of years, I came to understand or explain this puzzle. It made sense that this worked this way. It also made me realize there were much more effective ways to teach than what was being used in most of our courses. But it then also got me interested in starting to do science education research on my own, of doing experiments, collecting data, and looking for basic principles. So not so different from my traditional physics research. And, then also doing things like developing PhET as better tools for teaching. But in all of this time, sort of the main thing I've been thinking about is expertise. And in this case, what I mean is thinking like a good scientist or engineer, and what that means and how it's best taught. Now, I've been doing research on this for several decades now, but my context, my teaching and the education research I've been doing are institutions that are quite different, I realize, from most of yours, with different resources and constraints and students. And so I'm not going to go into much detail about what specific things we've been doing. I'll touch on that a little bit, but really I'm going to try and focus more on general principles about how the brain learns, what we know, and what this means in terms of general principles on what's the most effective teaching. So these are things that sort of go across a variety of educational contexts, and so hopefully it will be useful to you. So I'm going to start with a general introduction on how the brain learns complex thinking, what we know about that, and then what this means for teaching, how this kind of learning is best taught so that the brain learns most effectively. And that means, what the teacher needs to do. And I tested these ideas in many different courses now, but I'll just give one example from some of our research. And then I'm going to finish with how, since this is about PhET, say something about how I see PhET as supporting good teaching. So the most important thing that research is showing is really rethinking the process of how learning happens. And the old and still very widely held model, particularly at the university level, is that the process of learning starts with these student brains come into our classrooms and they vary in different ways. And we immerse them in knowledge in the teaching. And it soaks into different amounts depending on the conditions of those brains. And so with this as the model for learning, the focus is usually on selecting the best brains, trying to think of exams and measures and so on that they'll select who's going to be able to go to what institution, and then decide on what the knowledge soup that's going to give them, what topics are going to be covered in what order and so on. Now, although this model is still very widely held, research shows it's just wrong, and that the view of learning that we get out of research is that the brains come in, and at the university level certainly aren't very different, but at every level the brains are changeable, and that the education process actually transforms the brain, and what it does is it rewires how the neurons are hooked up in response to intense thinking. And this transformed brain has improved capabilities. So rather than thinking of filling a brain with knowledge, you need to be thinking about developing the capabilities of the brain. And we can see this in modern brain imaging, actually. Here's the brains of two people, and they're in MRI machines, and they're interpreting an X-ray image. And you can see how the brain of the expert radiologist, who's done a lot of this and is very highly trained in this, their brains are activated in a completely different way as a result of their training than the medical student on the right who's just learning to do this. So what brain research tells us really is that learning is about enhancing particularly the relevant neuron connections. And mostly the brain learns what it practices and not much else. But the brain development is also very much more like muscle development than we used to think. That just like if I want to build up a muscle, the intensity of exercise and the type of exercise, and I need to exercise that particular muscle in a very intense way, is critical for the development. And in the question of the brain, it's rather than physical exercise, like in a muscle, it's mental practice or mental exercise of the brain that's essential. And so the brain needs to be practicing. And so it's very much like performance in music or athletics, where one automatically knows that it would never happen without extensive practice. In learning, we need to have the brain practicing the learning, the thinking that you want it to learn. And so, but what education researchers are continually doing is looking for what's the most effective type of practice that will achieve the most learning in the brain in the minimum amount of time. And some of the work that I think is particularly relevant to this is Anders Ericsson pioneered. He studied the development of expertise across many different subjects, and he found that a particular type of practice is essential for the development of expertise, and he calls this deliberate practice. And he sees that it's the same whether it's in music or athletics or intellectual activities. And it applies really at all levels of expertise, that to improve, you need to have this deliberate practice, and how expert a person becomes depends very much on the amount of deliberate practice, really more so than any other measures we can find about innate capabilities. So what is this deliberate practice that Ericsson says is so important? First, it's important to know that it's not routine, low-level practice or just getting experience. It's actually much more intense, focused practice. And it's focused particularly on improvement in what one's doing. And it's focused particularly on improving the sub-skills. And so one needs to have the sub-skills of expertise that are to be mastered. And if you think about what a music coach or an athletic coach does, they break the subject down into, a musician. There's particular ways to hold their hands, to hold the instrument, and all these make scales, all these details that really identify the little pieces of expertise, and then the learner practices these intently and getting better. Now, in science and engineering, the expertise, I'd argue, that we're after is really the technical problem solving and the thinking that scientists do when they're carrying out technical problem solving. And so this is the expertise that they need to practice and master. And I'll go into a minute into what we see as the sub-skills of that. But let me finish with deliberate practice. So another component of deliberate practice that's quite important is that the learner isn't just practicing, they're also getting feedback from a coach or teacher on how to improve and how to do better. And it's also been identified that motivation is very important, in that serious learning, this kind of serious, intense practice in whatever area it's in, requires hard work. And in the teaching of learning of science, it's hard mental effort. And so when the learner really has to be motivated to put in that effort. So this deliberate practice really identifies what the learner needs to do to develop expertise, to develop the thinking capabilities we want. And so what does the teacher do? Well, the good teaching is really facilitating deliberate practice by the learner. And I have to say, lecturing doesn't provide deliberate practice. There's very little mental work that the student does when they're just sitting listening to a lecture. And so that takes me to then what's a better way to do it. What the second part of my talk then is what the teacher needs to do. And as I said, I've tested this in many different courses now and collected the results on the learning outcomes to show that it is more effective. So the first thing the teacher needs to do is create good practice exercises. These are, engaging, challenging problems that the students work on to practice developing their thinking. And the second thing is that teacher needs to think about how to implement these in the classroom, and so that the students are fully engaged in the thinking practice that you want them to learn. And then the third thing the teacher needs to do is provide good feedback. So that means there's several aspects of that. It needs to be timely while the student still remembers that how they were thinking. It needs to be specific in telling the students exactly what they need to improve. And then sometimes it needs to be providing them with new information. Once they see they have a problem, providing the information that they realize now is needed and how to apply it. So going into a little more detail then about what's involved in thinking about a good practice exercise or task for students, you want them to be practicing the thinking that you want them to learn, that using the reasoning and knowledge of scientists to solve a problem. But just solving, if you just talk about problem solving, that's a very complex activity. It involves a lot of different things, a lot of different parts. And so it's very challenging to learn it, especially if you're just told to go off and learn to do this. It's sort of like being told go off to, learn to play tennis well or play the violin without any sort of identification of what parts to do and how to go about this in a manageable way. And so my group has done research on technical expertise that I think provides guidance for how to identify better the pieces of problem solving to be learned. And this came from our research where we looked at a large number, about 50 very skilled scientists and engineers and some medical doctors, and we looked in detail at how they solved authentic problems in their disciplines. And we discovered that their problem-solving process was really defined by making a set of decisions. And the thing that was most striking, we were able to identify 29 specific decisions they made. But there was really, what was most striking was the same decisions were used in virtually by all these experts across all these different disciplines of science and engineering. And so that may sound very surprising if you think about how different these disciplines of science and engineering are, until you look at what the decisions are. And there's things like deciding on what concepts and models are relevant to a new problem, deciding what information they need and what's irrelevant, and deciding how to find that information that's needed, deciding what simplifications and approximations are appropriate, deciding how to break the problem down into separate pieces to tackle. And then once they find information, deciding on how reliable is the information, deciding on what can be concluded from it. And then there's sort of what we call reflection practice of thinking about, do I have all the information I need? Is my approach working? Should I change some way I'm tackling this problem? And so while we see these are key steps in technical problem solving, I think you can realize that actually these are good decisions that a person could guide many decisions that a student makes in their future life. Now, although the decisions are common across all these different disciplines, actually how the decisions are made is quite different, and that is very dependent on the context. And so the actual making of each of these decisions requires specialized disciplinary knowledge appropriate to that context. And so we see that these experts have knowledge, but what's important about their knowledge is the knowing when and how to actually use that knowledge to make problem-solving decisions. Now, I'm not going to take time to go into each of the 29 decisions. I'm just going to put them up here very quickly for you, and you can sort of see the general categories. There are things like setting the goals and general approach to solving the problem, thinking of potential solutions, and decomposing it into parts, deciding on priorities, what things are most difficult, what things to look at first, deciding what information's needed, and plans to go about getting information. Then once you have information, there's decisions about how to analyze the data and how to represent it, how reliable it is. And then, does this make sense? Are there anomalies? What conclusions can be drawn, etc.? What's the best solution based on what you've learned? And then I mentioned there's several reflection decisions, and one sort of examines how well this is working, how well the approach is working, are there additional things needed? And then there's some final decisions about presentation of results and what their implications are, who the audience is, and how to present that work. So, of course, that's a lot of things to cover, and to become a skilled scientist, a learner really needs to practice and master all of them, but you're not going to do that in every course. And so in thinking about what you would look at in an individual course, you need to have some selectivity about what you want the students to actually pay attention to and focus on. And so here's a useful subset of decisions that we've arrived at that we actually are then where there's a few decisions about students when they're first given a problem, setting the goals of the problem, framing the problem, and planning their solution approach. Then a few decisions about inquiring and interpreting information they need, and then choosing solutions, executing based on that, with some amount of reflection along the way, thinking about, okay, is this working or do I need to make changes? And so we've been using this as a template, basically, as students to follow. With they're given practice problems to solve both in class and then on homework, and they follow this template of making these specific decisions, and try and give them interesting, realistic problems that really require making these decisions. And in the context in which we've been using this mostly in courses, we have students working in small groups in 3 or 4, and they have to fill out worksheets that provide answers and their reasons for the answers. And basically they, working in these small groups, help each other learn. So the general approach that we found of implementing this kind of deliberate practice teaching in classrooms that have now been applied across many different subjects and course levels and class sizes is shown here, where you have students do some kind of modest preparation before class, and the instructor designs the practice problems, the activities they want students to carry out in class, and then what students are given those, and then they work in these small groups working through the activities, and they might spend 10 or 15 minutes on doing some particular part. While they're doing that, the instructor's circulating around, monitoring those groups, listening to the conversations, seeing what answers students are actually giving, and sometimes answering individual questions. And then as an appropriate point in the stopping point in the activity, then the instructor will call the whole class together and basically, provide them with feedback on things they're doing right, places where they see they're going wrong, they need help, or they need new information. or answering questions. And so that'll then go on for a little while, and then the students will then return back to their activity working through that. And this just the entire class period is then just based on this practice with feedback. And the essential features of this kind of teaching are that the students are thinking, they're practicing the expert reasoning that you want them to learn. And the instructors are much more knowledgeable about their thinking, since they're actually able to kind of observe the thinking and performance in real time. That allows them to be much more effective teachers and provide more effective feedback to the students. So I said I wasn't going to go into details about it, all the experiments we've done in classes we tested this in, but I do want to give one example that shows the pretty dramatic benefits to teaching this way. This was done in a very large introductory physics course where we could take two sections of a course which had almost 300 students each and measure those to be essentially identical populations in the two sections. And then the two sections were taught in different ways. The control section was taught by a highly experienced, well-rated professor but used a standard lecture approach of essentially telling students the material. And the experimental section was someone who was a fairly new PhD, but had been trained in my program in these deliberate practice teaching principles. And so they agreed to cover the same material in the same time, and then had a surprise exam to follow up on this to see just what students had learned just from their classroom. The timing was such that students weren't doing homework or studying for exams in this time. It was just so this could measure just how much they were learning from the classroom experience. So the students in the experimental class did the things that I already talked about. They had questions they had to answer. They would discuss in a big class like this, just the neighbors sitting around them while the instructor was listening into those discussions and then providing feedback to the whole class periodically. And on the test that was given then to both sections, here's how the scores compared with the score on this axis and the number of students on that axis. And you can see the experimental class scored much higher. And the thing I want to emphasize is two parts. One is the learning from lecture was very small in this case, and as we've seen in other data. But more than that, the blue curve, the entire distribution is shifted up. So this says that this isn't a kind of teaching that's just better for the weaker students or just better for the strong students. It's better for all the students. Everybody improves in their learning. Now, I'm going to dig into some pretty sort of specialized research on student decision making that we've carried out that is relevant to thinking about teaching on this. And the first is the need for the student, what we call student control or agency. And that, what I mean by that is that we did a study where we compared the students were told these are decisions you have to make, but they had to make the decisions, as opposed to being told by the instructor, here's the decision needs to be made, and here's what the decision should be to be most effective. And then so we divided the student population was divided in these two different treatments, and then we measured their performance on later related tasks. This was an introductory physics lab, so it was their later tasks of how to design and analyze experiments. And we found enormous differences. The students who actually were practicing making the decisions were just much, much better at learning. You know, they had learned the things you wanted them to be able to do much better than the ones who were actually told what the decision should be. Now, we did another study where we looked at the standard course exams and textbook kind of problems to ask how well are these kind of problems giving students practice in making these important problem solving decisions, what we need them to learn. And what we found is that if you look at the typical textbook problem, that nearly all of the decisions that are needed for solving any authentic real world problem that the students are going to be confronted with, nearly all of these decisions are removed from the typical coursework or textbook problems. And they're removed because the problems, for example, tell the students what assumptions to make, what concepts to use. They give them all the information needed to solve the problem and only that information. And all of these things are in realistic problems that students might be confronted with in their future careers. These are all absolutely essential and needed for all of those problems, but here they're removed from what they practice. Also, many problems are decomposed into parts for the student in principle to make them easier, but in practice it just means the students aren't learning that. And so what this shows is that students are learning information, but they're not learning how to use that information in any meaningful way to solve problems. And if you get back to the original puzzle I had about my PhD research students, that was their problem. They had been through all these courses that they learned in physics information, but not how to use it to actually do physics. Now, the other thing from our studies showed that the experts really organize their knowledge around how it's being used to make decisions. And so what the implications of this are for teaching is that it's best to give students problems that require them to make decisions. But they need knowledge about the subject to do this. But the best if they learn that knowledge in the context of how it's actually used to make decisions to solve problems, as opposed to just being told, here's a bunch of stuff we know about science. It's going to be useful for you sometime. It's much better to say, here's stuff we know about science and see how it allows us to solve these problems or answer these kinds of questions. Okay, so let me turn to the last part of how PhET can help support learning, or how I see as. And the first is that it's a better way to present knowledge. That there's conceptual models that show the important factors in some scientific situation and how these factors interact. And what we see is these kind of conceptual models are really the way scientists organize their knowledge, and how they think about knowledge and how they apply it. And so what PhET simulations do is they really provide a more effective way to present scientific conceptual models. They show explicitly what factors are important, how they're related. It allows the students to visualize the invisible and the dynamics of what's happening in very much the way scientists see this, but it's very hard to translate just a verbal description into that kind of thing. The simulations make it much easier for people to understand to visualize and think about these. But also they allow students to explore and discover the relationships and behaviors on themselves by playing with changing factors and see what happens. This just gives them as a more just effective way of learning. And so I assume this group was all pretty familiar with them, but I'll just for the sake of completeness, give an example of the circuit construction kit here, where students can build circuits, see what happens what's necessary to make a light bulb work out. And I think it's worth recognizing that these simulations are a way, they're a kind of artificial intelligence. Everybody's talking about artificial intelligence in education these days. And they generally are thinking about large language models, and which PhET simulations aren't, but what they are is still something where the student acts and the simulation responds based on an underlying algorithm. And so that really is artificial intelligence, and it's part of what makes them effective here. Now, one implication of what I was talking about before, though, is also that I believe, and I think we would have some research showing this, that the simulations are best used not by just telling students to go to the simulation and learn things, but rather giving them some guiding question to structure their exploration and investigation of, and thinking about how what the simulation shows can be used. And so, for example, in the circuit construction kit, asking students to go and use the simulation to figure out what are the conditions needed to light up a light bulb. Or in the buoyancy simulation, for example, asking them what determines if an object will float or sink as a guiding question for their exploration. Now, there's another aspect to how PhETs are effective, and that is they're more engaging than other ways of teaching, so that they get students' full attention. And I talked about that a little bit when I was talking about deliberate practice, attention being so important. But I want to go into some more kind of the cognitive science details of this, because it's something that cognitive scientists have studied a lot, and teachers aren't very familiar with it, but it's really relevant to learning. And that is to look at how the memory works. And in fact, the memory is composed of two, the way cognitive scientists think about it, is two kinds of components. There's what's called the long-term memory, and this is what most of us mean when we talk about memory. This has a very large capacity and very long duration. You remember many things, and for years or decades. But in addition, there's another aspect of memory called the short-term working memory. This is kind of a buffer in which information has to go through before it can be processed and go into long-term memory. This short-term working memory is very different. It has a very small capacity, typically for the human brain, 5 to 7 items. It lasts for timescales of minutes. It's essentially what the brain can pay attention to at any given time. And because what this very limited capacity means is that whenever the brain hears or sees something new, pays attention to something new, it pushes out something that was in the short-term working memory. And so that thing that get pushed out never get processed or into long-term memory. And so what's shown in cognitive science very repeatedly is that anything that puts more demands on the working memory, it causes less processing and less learning. And so anything that gets students' attention has a cost in terms of the learning, and particularly so anything that gets attention that's not directly focused on what you want them to learn is going to be harmful. And the most dramatic example of this is split attention. So when the person is splitting their attention between two different things, it just is a disaster for learning. And so the common example of, frankly, nowadays is students, if they're checking their phones during class, it's just terrible for impacts on how it hurts their learning. And the reason this is particularly bad is that humans in studies it's been shown that they're really poor at recognizing how bad splitting their attention, trying to multitask is in terms of the impact on their thinking and learning. And so it makes the point that if you want learning, it's really critical to think everything you can do to get the students full attention on what you want them to learn and avoid any other distractions. And so what that means is if you're thinking of practice tasks for students to work on, you want them to be engaging and challenging so that they'll feel that they both need and are willing to put full attention into doing them. And then I talked about PhET tasks, PhET simulation tasks. They're much more engaging. The students are changing things, seeing how it happens. And so they tend to pay much more attention than they will to just listening to something. And so this fact it gets them more focused and more attentive makes them more effective for learning. So with that, I'll finish up here. I talked a lot about how research shows good design and implementation for teaching, some general principles, and why these are better than traditional lectures approach, with the key ideas being the brain really learns what it practices, and good learning is developing the brain, developing new capabilities. And here's some of my favorite references in books if you want to learn more about this. And I'll also, I think Diana has translated my slides and make those available. So thank you for your attention, and I can answer questions now. I think you need to put in chat and then Diana will translate for me.
Yeah, thank you very much for your presentation. Very interesting, everything that you have presented. Well, while people is sharing with me the questions, I really have one. Well, I have several, but one for me, the most important. You know that I am the Latin American ambassador of PhET, and my work is to try to make this, to reach the most teachers that I can, that we can. And I would like to know if, I'm going to play my questions here. You share about transforming classes in real problem-solving spaces. Are there any countries or projects already trying to implement this approach to a large scale, maybe in a city or a national level? Who is leading that work and how?
I don't know of anybody who's really trying to do this at a national scale. But that's not necessarily saying that it's not being done. I don't think I'm that tremendously well informed about this. But I would say generally, I think these ideas are still pretty new and pretty radical. That the idea of teaching by just telling people things, lecturing at them, is awfully well established and been used for a long time. And so it's going to take a while, I think, to kind of get a broader shift from that thinking, even though we've got very good data now showing the kind of teaching I'm talking about that it's superior. I think it still takes a while to get implemented.
Well, we're still working then. I have another question I write it in the chat, and is how you think the simulation help a teacher diagnose students' thinking in real time and provide the target feedback that this model of deliberate practice requires?
So, yeah, I mean, that raises interesting questions about what you could learn from seeing what students are doing with the simulation. So, you know, if you can actually observe what students are doing, you can see what kind of questions they're asking themselves, what kind of changes they're making, and what they're thinking about as they're doing. So, you know, this kind of work is done as part of the development of simulations. They're tested with real students. In a classroom, I think, well, in the future, we're the PhET program and with some collaborators just starting to think how to use artificial intelligence to sort of allow a teacher to get a better idea of what students are doing with the simulation from, you know, many students at once. But until that technology gets developed, I think it's the best a teacher can do is really to just go around and try and observe what the students are doing, you know, if they're in small groups, what they're talking about, what they've seen, or what questions they're asking, and learn, you know, that's kind of old-fashioned way, but that's, I think, the best we can do right now. A teacher just has to kind of observe what's being done.
Yeah. Here is another question. How does make these far-reaching changes to the way so many teachers around the world teach impact your life as a physicist and educator? We want to hear about your heart.
I mean, you know, I do this because I think it's very important, and I switched. I was doing kind of physics research and education both, but I reached the point where it seemed like the education work was just more important, that I had opportunities to make contributions there that would affect many more people and in a broader way than what the specialized physics research I could do. So that shifted me to more into getting more involved in just focused on the education work. But, you know, I'd like it if I could make a lot bigger, broader impact, you know, but I do what I can.
And you are doing a lot. We have this other question. How does PhET contribute to the learning of the most disadvantaged students in vulnerable areas like Latin America? If you know something.
Yeah, so, I mean, I'm pretty removed from that. You know, you're probably better able than I am to answer those questions. But, you know, what I've seen and been very happy about is that there are places in Latin America and in Africa where the students just have very little resources, but they do have PhET simulations that can provide them with more education, you know, more useful educational experience than these students. And, you know, a lot of times they can have access to PhET simulations when they have very few other educational resources that actually can help them. So that's I think a real value that I'm very, very pleased that it can provide.
Thank you. This is another question. In Latin America, we are promoting STEM learning, interdisciplinary projects, and that tackle real social issues like population and sustainability. Do you think it's possible for a student to achieve the rigorous physics learning through this kind of contextualized STEM projects, or a physics learning need a physics class?
I think, I would say you can learn a lot of physics in a class that's not just physics related. I mean, I think when you look at these bigger, broader questions and problems, they still involve if you kind of think about the things I was telling you, they involve the same kind of decisions. And so you need to make a lot of those same decisions, but then you need to think about what knowledge you need to apply to making those decisions. Some of that knowledge, and if it's in sustainability or something, there's a bunch of that knowledge that's going to be physics. And, if you introduce the physics in that context, they can learn the physics just fine without it being in a physics class. And so I would say, yes, you can make these kind of broader science education issues and courses and projects that are very effective actually at also teaching the very detailed disciplinary knowledge. Just thinking about the context in which it's used.
Perfect, approved. We have another fan of STEM education. Have you found difference between students of physics and engineering in a form of learning?
I haven't actually. I in the last several years, I've gotten involved in somewhat more in engineering education as well. Before I was doing more physics, and what I've seen is there's a much more of a focus in engineering on designing things, and so that's a different kind of thinking than we usually call upon physics students to do. But in terms of the way students think, the way they learn, I've found them actually to be very similar. And that makes me think that if we could teach science and engineering courses in a more consistent way of thinking about in all the different courses how you need to make certain problem-solving decisions about solving it, how it would actually help people learn across different courses much more effectively, because they'd realize how certain aspects of their learning apply more generally.
Perfect. And from engineering, we are moving to elementary school. Have you imagined that when you launching the PhET simulation for university students, they will eventually be used for teach children in early childhoods and primary education, and even be adapted to research students with neurodiversity? This is from Leila, preschool teacher.
Yeah. So, when I first got started in developing PhET simulations, I did notice it started out with me using some simulations to explain my physics research. And I was really struck by those simulations working with such a very broad set population. I could use the same simulations explaining my research to a bunch of physics professors as I could with at least middle school students anyway. And so that was one of the things that attracted me to the idea of developing simulations for teaching, is having seen that they did seem to work for such a wide range of populations. Now, I never imagined PhET would become nearly as big and successful and widely used as it has been. And most of the credit that doesn't go for me, it goes to Kathy Perkins, who took over and is running it for many years. But so I never imagined that it would be so successful. But I did realize from the beginning that simulations were particularly unique in how broad an audience, set of learners they could be effective for. And just to get into a little more technical detail about that, I think a lot of that has to do with the fact that in a PhET simulation, the learner is in a sense asking their own questions. They're making decisions about what they do, what they change, what they look at. And so that allows them a level of control of the learning process, which you don't have in other education settings. And so that level of control means you can adjust it to looking at more complicated things and so on if you're ready for that, but it also means you can do much simpler things if you're just trying to understand, if you're much younger and don't know very much, how that can be valuable for you. So I think that this just emphasizes, I think, the value of educational control to setting a level that makes simulations effective, but it's sort of important lessons about teaching in general.
Well, we have several education researchers here today, some starting and others very experienced. From your point of view, what are the key questions we still need to reach? Where should we be focusing for our efforts now?
Boy, that's a big question. I think I can answer the question in different contexts. What I would say is one of the questions we have is that most of, certainly in physics, but also in science education in general, I think most of the good data we have comes from large North American universities. And so that's a limited set of students with certain, defined characteristics. And so one of the things is kind of understanding better a broader population of students and exploring methods and learning for students across a broader variety of contexts and backgrounds and so on. So, that's one area that I see is particularly useful. So that's sort of doing similar things, but just looking at different populations. But then there's also areas that I think still remain to be explored. One of the ones that is I always think about it is just homework. We think about homework as used in different courses in different ways, and it's such a pervasive thing, but we really have very little research on what's the most effective ways to do it, what value it provides, and how you can enhance its value, for example. So that's just an example of a big aspect of teaching that remains to be studied and figured out what's the optimum.
Perfect. Last question for closing, a very general. What do you recommend for teachers, educators to develop competencies in inquiry-based teaching and active learning with PhET?
Oh boy, I don't know more than the things you organize, things like this conference. If I knew better things to do, I would be working on doing them. But that's a question that's beyond my knowledge, I think.
Continue participating in the PhET activities.
Exactly, yes, and try.
Well, thank you, Carl, for this amazing presentation and this time to chat and solve some questions that the public have. Well, you always are a person that is very open to collaborate with the Latin American community. Then I know that we are going to have you in other events. Thank you. Have a great weekend.
Okay, thank you. It's a pleasure talking to all of you.
Y para todos los que nos acompañan, el evento del Congreso PhET no ha terminado. Seguimos con los talleres dentro de una hora. Tendremos 10 talleres, todos en nuestro sitio web del Congreso, que espero estén poniendo en el chat de YouTube para que nos acompañen, ¿no? Es ir a la página de los talleres, checar de qué trata cada uno de ellos, elegir el que tú más quieras y unirte. Si participaste ayer, son los mismos talleres que ayer que se repiten con la idea de que al menos participes en 2 talleres diferentes durante este congreso. Entonces, 1 hora de descanso y nos vemos en 1 hora para la sesión de talleres. Muchas gracias por acompañarnos. Nos estamos viendo. Al parecer había un error No, creo que ya estamos arreglando para que, había un link mal, pero ya lo estamos arreglando para que cuando entres al taller que quieres, te mande a esa sala. Ahora sí, nos vemos. Muchas gracias a todos.